In the last few years, artificial intelligence has made leaps that once seemed like science fiction. But behind every breakthrough, whether it's generating lifelike images, writing coherent essays, or composing music, there's a foundational shift in how we think about learning, memory, and reasoning in machines. At the heart of this transformation lies a single architectural innovation, the transformer. You've probably heard the term transformer in the context of large language models like GPT, Claude, or Llama. But what exactly is a transformer, and why has it become the dominant force in modern AI? To understand that, we need to go back to the beginning. Before transformers, the state-of-the-art in sequence modeling was the recurrent neural network, or RNN. RNNs were designed to process sequences, like sentences, time series, or audio, by maintaining a hidden state that carried information from one step to the next. The idea was elegant. Each new input would update the hidden state, which in turn influenced the next output. But this approach had a critical flaw, the vanishing gradient problem. As sequences got longer, the model struggled to remember information from earlier steps. A sentence like "the cat that the dog chased ran into the house" might lose track of the cat by the time it reaches "ran," because the signal from the beginning had faded out. Then came the LSTM, long short-term memory, designed to solve this. LSTMs introduced memory cells and gating mechanisms that could selectively retain or forget information over long sequences. They were a huge improvement, and for years, they powered everything from speech recognition to machine translation. But even LSTMs had limitations. They processed data sequentially. Each step had to wait for the previous one to finish. That made training slow and inefficient, especially on long sequences. Enter the transformer, introduced in 2017 in a landmark paper titled "Attention is All You Need." This model didn't use recurrence at all. Instead, it relied entirely on a mechanism called self-attention. Let's break that down. Imagine you're reading a paragraph. Your brain doesn't process every word one after another. Instead, it jumps around, connecting the cat to chased, ran to house, and dog to chased all at once. That's what self-attention does. It allows every position in a sequence to attend to every other position, measuring how relevant each word is to every other word. Mathematically, self-attention computes a weighted sum of values, where the weights are determined by the similarity between queries and keys. Given a sequence of words, each word becomes a query, a key, and a value. The model calculates how much each word should pay attention to every other word by comparing their keys and queries. The result? A new representation for each word that incorporates context from the entire sequence. But here's the real game changer. Because the attention mechanism is fully parallelizable, the transformer doesn't need to process tokens one at a time. It can compute all the attention scores across the entire sequence simultaneously. That's why transformers train so much faster than RNNs or LSTMs. Now, a single self-attention layer isn't enough. Transformers stack multiple layers, each one refining the representations. But there's more. Inside each layer, there's also a feed-forward network, which acts like a kind of local processor, transforming the attention outputs with nonlinear operations. And to help the model learn complex patterns, it uses residual connections, skip connections that let gradients flow more easily during training. But how does the model know what to pay attention to? It doesn't just rely on raw text. It learns to assign attention weights during training, using a massive amount of data. As it processes billions of sentences, it discovers patterns. Pronouns refer to nouns, verbs describe actions, and clauses depend on their subjects. These patterns emerge not from explicit rules, but from statistical regularities in language. Now, the transformer isn't just for language. It's been adapted to vision, audio, and even protein folding. In vision, for example, images are broken into patches, like tiny tiles, and each patch is treated like a token. The model then applies self-attention across all patches, learning spatial relationships just as it learns syntactic relationships in text. This is how models like vision transformers, ViT, can match or exceed the performance of convolutional neural networks, despite having no built-in notion of local spatial structure. And in protein folding, models like AlphaFold use attention to capture long-range dependencies between amino acids, which are crucial for predicting how a protein folds into its 3D shape. So why does all this matter? Because the transformer isn't just a better model, it's a new paradigm. It's shifted AI from sequential, state-dependent computation to parallel, context-aware representation learning. It's enabled models to scale in ways previously impossible, leading to the massive language models we see today. But it's not without cost. Transformers are computationally expensive. They require enormous datasets and massive amounts of memory, especially as sequence length grows. The attention mechanism scales quadratically with sequence length, so doubling the input length increases memory usage by 4 times. That's why researchers are now exploring alternatives: sparse attention, linear attention, and hybrid architectures that combine transformers with other models. Still, the transformer remains the backbone of modern AI. Its ability to capture global context, process data in parallel, and scale to massive sizes has redefined what machines can learn. And as we continue to push the boundaries, exploring multimodal models, reasoning systems, and even artificial general intelligence, the principles of attention and parallel representation will remain central. So the next time you ask a model to write a poem, summarize a document, or explain a complex concept, remember,